Hello, everyone. So my name is Rytis. I work at Vinted at production engineering domain and foundations team. And today I would like to present the data center network that we have at Vinted. So the agenda is at first we'll talk a little bit about our network topology, the scale. Later on we'll talk about how we manage the network, the automated tests, the Ansible part, and later on we'll talk about the network services that we provide to our organization. After that, we'll talk about the network operating systems that we currently use and support, and we'll finish with a summary. So let's go on to introduction. So at our data centers, we're using class topology. To those who don't know what that is, it's a multi-tier, multi-stage topology providing high availability. So it is every network, every rack in data center has a leaf switch that connects to two or more spine switches, and that is considered a network pod. So with this two-layer class topology, you're limited to the amount of racks. The amount of racks is limited to the amount of ports on spine switches, and if you run out of that, you can introduce a third layer called super spine layer and introduce another pod. So currently we have 3 data centers, 3 locations, and across all those 3 locations we have more than 150 racks and almost 200 network devices. So every rack has its own layer 2 network, and we start routing on the leaf switch. And to exchange routing information, we use BGP unnumbered, and every leaf pairs with every spine and exchanges routing. So every switch has its own autonomous system, and our racks are quite autonomous as well, because we can disconnect it from the spine it is connected to and move it to another location, connect it there, and it would work with no issues. Okay, so let's move on and talk about how we manage the network. It's not surprise we use Ansible to configure switches. We group our configuration based on the function it defines, not by device. So we have so in that case, we can easily look up all the interface configuration, all the peerings that we have across all data centers. And this configuration is independent of the operating system that the switch is running on. And it gets translated when we push the config to switches. And it also is supported on Cumulus and Sonic switches. Okay. We started from the beginning with managing our network as code and pushing without any manual changes. So in order to prevent issues, we wanted to do continuous integration and testing on every change. So we needed to have easy to set up testing environments. So in order to have that, we needed to create topologies easily. So we are defining our topologies for testing in graphwiz.syntax. You can see the example on the top left. So you define a device, you define a port, and you define to which device and port it is connected to. So this kind of syntax is then converted into a vagrant file by a topology converter, a tool provided by Cumulus Consulting. And it then creates a vagrant file that brings up all the necessary virtual machines using libvirt. And interconnections between these VMs are made using UDP unicast tunnels, so you can have pretty much, you can have a lot of them on every server you want. So we use up to 30 VMs with up to 100 interconnections in some test environments, but you can go really high and have much more. In the bottom left, you can see the test topology. Bottom right, yeah, the test topology. It's a very simplified topology, yeah, we have like a management switch that interconnects all the devices. You can connect to them via the management VRF. And we have a host that is connected to this management interface and runs Ansible, and we execute tests on it. So yeah, now let's move on to how we do testing. So we use Sync Auditor, previously known as Inspec. So a bit of background, we are using Chef for our server infrastructure to manage it as code, and it uses Test Kitchen and it uses Inspec or Sync Auditor. So we decided to use the same for our network. That's why we chose this. So basically, this Sync Auditor connects to the Ansible host and executes the necessary tests from there because it has all the connectivity to all the switches. So it utilizes SSH, HTTP, other protocols together to get the current state of the topology, and then compares it to the defined state that we want to achieve. So also we had to write some custom resources for Sync Auditor because it was focused on servers and it didn't have many resources that would get the network information for us that we needed. So one of examples is this net BGP route that you can see on the bottom right. So it checks for routes in certain VRFs. It can't compare next hop count, the next hops itself, and it just fails if it's not there. So also what we do is we imitate failures of some devices or some links in these testing environments to see if our network converges quickly and does not impose long downtimes in case of a failure. Okay, so let's move on to the network services that we provide to our organization. So we use Anycast in a lot of places, and it means that we advertise the same IP address from multiple servers, and clients get routed to the closest one. So a lot of services high availability is implemented using Anycast. So this gives a couple of advantages. So first of all, it routes the clients to the to the closest one, to the closest server. So you are sure that clients don't go to the other data center if not necessary, and it doesn't increase the latency. Another advantage is that it provides high availability. So servers have BGP sessions with leaf switches, so in case server goes down, BGP session also goes down and the advertisement is withdrawn. So the traffic gets shifted to another server. And also, since we use ECMP, it handles the load balancing part. So yeah, we use this for NAT, front reverse proxies, PXE servers, and a lot more. Yeah, so a lot of, almost all of the applications run on Kubernetes, so we had to integrate them into our network as well. Kubernetes uses its separate IP address spaces, so it had to be integrated using BGP. So all the Kubernetes workers have BGP sessions with our leaf switches, and they advertise two ranges. So SVC IP range, it's Anycast range, the same advertised from all the workers in the same cluster, and the pod IP range, it's unique per worker and is assigned to pods inside that worker. So yeah, and in case you are accessing some service in Kubernetes using its service IP, the traffic gets routed first to the closest Kubernetes worker, and then Kubernetes does its magic to load balance the request to the worker that hosts the pod serving this. And yeah, now I would like to talk about the issue we had with this service IP. So this is the free tier class topology. We have a superspine there, and at one point we had all of the Kubernetes workers in pod 1, and all of the traffic going to service IPs would go to superspine to then spine X in pod 1 and get distributed there. But at one point, the Kubernetes team launched a few servers, like 2 or 3, I think, on pod 2. And it advertised service IP addresses, and it got advertised to superspine. And suddenly, the traffic gets split 50-50. And since the traffic was really high, the Kubernetes workers in pod 2 couldn't cope with the load. And their network cards were saturated, so the error rate was elevated. It was kind of difficult to understand what was the problem at first, but when we got the hang of it, it was quite obvious. So now we don't have this problem anymore because our front servers are not accessing the services via service IP. They use pods, pod IPs, because we use Istio with Envoy as reverse proxies. So yeah, we don't have this problem anymore. So another interesting case where we used Anycast was database sharding. So it's a situation when your database is getting too big and it's getting slow, so you want to separate some tables and move it to another group of servers. So in order to do that, we first would introduce the new database connections in the clients or applications. So you can see here the green one is the old connection used to access everything in DB1, and the blue one is the new one. So the green one connects directly to the database host, to its IP address, and the blue one is connecting to the Anycast IP that the DB1 is advertising at the moment. And the database replication is set up to copy all the data to DB2 host. And at the cutoff time, we have to execute this pretty carefully to not introduce writes where they are not meant to be and to not corrupt the database. So we have to stop advertising Anycast AP on DB1, perform all the transactions, then make sure that replication finished, cut off replication, and start advertising Anycast AP on DB2. This way, all the clients seamlessly reconnect to DB2, and we don't need to change configuration or redeploy our apps to do that. So yeah, this was used until we started using Vitess that handles all the database sharding now, so we don't need that anymore. Okay, another service that we used is EVPN. So it is a service allowing you to have like an overlay network on top of your underlay fabric. And we used to have it for our externally network-facing servers. So we would configure virtual tunneling endpoints on the leaves and exits. So in this case, our server 1 and server 2 can have IP addresses from the same external network range and have exit switch as their gateway. So we could bring this to any rack in any DC, and it was very flexible for us to introduce new hosts. But however, this technology brings a lot of complexity, and it was pretty hard to troubleshoot when we faced issues. So we decided to decommission it, and we don't use it anymore. Okay, so let's move on to network operating systems. We started off with Cumulus Linux because it was, at that time, it was Linux-based network operating system that supported multiple hardware vendors. So it was saving us from vendor lock-in, but NVIDIA acquired Cumulus, and the support for Broadcom ASICs stopped. So it was kind of a vendor lock-in because we had to buy the operating system and the hardware from the same vendor. we were looking for a solution to that and found Sonic, so decided to move with that. And Sonic is currently supporting multiple ASICs, multiple hardware vendors, and is saving us from vendor lock-in. So we use community version of Sonic, and we build our image in-house, as we had some issues with the pre-built images, so we had to fix them. Also, we use both of these operating systems in our testing environment I talked previously. So some of the switches are Cumulus-based, some Sonic-based, and this way we make sure that we don't break anything. Interoperability, there are no interoperability issues, and Ansible playbooks run on both. Okay, so let's move on to summarize. So I believe that the network at Vinted is as scalable and as easy to maintain because of these three reasons. So firstly, we started off with network as code from the beginning, and it allowed us to not have like any special devices or special engineers who only knew how to configure things, and also it makes it easy to replace a switch in the middle of a night, so anybody can do that. Another thing is this automated testing and easy to set up test environments. So automated testing prevented many production issues, and yeah, helped us with that. And the easy to set up test environments also allowed us to learn by doing. We would set up a test environment, learn a new approach, a new topology, and move to production when everything is well tested. And we don't provide any unnecessary functionality in the network. We make it as simple as possible, and in case some feature is necessary, we want to move it to a higher level in the stack, and for us, Istio service mesh solves many problems for that, and we don't need to move them to the network. So I believe these three things are the main reason that we still don't have a dedicated network team at Vinted, and we as Foundations team manage this besides hardware and other stuff that we have. And that's about it. Thank you.
Thank you, Rytis.